Light travels in a straight line. You already knew that, right? You learned it when you were maybe 6 years old. Somebody gave you a flashlight, one of those big heavy ones with the metal casing, and you turned it on and pointed it at the wall, and there it was, a bright circle, and you could see the beam going straight from the flashlight to the wall. No curves, no wiggles, a straight shot. Or maybe you were lying in bed early one morning and you noticed a sunbeam coming through a crack in the curtains, cutting a bright diagonal line across the room full of dust, floating and glowing, and it went absolutely straight from the window to the floor. Not a single bend. And you thought, sure, light goes straight, 186,000 miles per second. It leaves the sun, crosses 93 million miles of absolutely empty space, not a single atom in the way for most of that journey, and it arrives at your face, 8 minutes and a handful of seconds, simple, clean, done. And if I asked you right now, how does light get from point A to point B, you would tell me, well, it travels. It moves through space, like a little bullet, a tiny golden pellet shot out of a flashlight. You might even use the fancy word photon, little particle of light zipping along in a straight line at the maximum speed the universe allows, minding its own business. And that picture, that image of a little golden bullet, is completely wrong. Now, I am not calling you stupid for believing it. You are in spectacular company. Isaac Newton believed something very much like it. He called them corpuscles, little grains of light, and he had excellent reasons for thinking that way. The man was not a fool. He was one of the greatest minds in the history of the human species. He noticed that light makes sharp shadows, and you only get sharp shadows from things traveling in straight lines. If light was some fuzzy spreading thing, shadows would have blurry edges. But the shadow of a coin is sharp, the shadow of your hand is sharp. So light must be going straight. Newton also noticed that light bounces off mirrors at perfectly predictable angles, just the way balls bounce off walls. He could calculate reflection perfectly with the corpuscle picture. And for 150 years after Newton, most of the best physicists in the world worked with this picture and got excellent results. So the wrong idea is not a dumb idea, it is an extremely smart idea. It just happens to be wrong in a way that nobody suspected for a very long time. What I want to do today is take you on a journey. I am going to build up the bullet picture until you feel completely confident in it. I am going to let you sit in the warm bath of certainty, and then I am going to pull the plug. Let us start with what the bullet picture gets right, because it gets a lot right. Shadows. You take a lamp and hold up your hand. The little bullets of light fly out of the lamp in every direction. The ones heading toward the wall behind your hand get blocked. Your hand is opaque. The bullets stop at your hand and go no further. Behind your hand, darkness, a shadow. The shape of the shadow matches the shape of your hand because the bullets are going straight. If they curved, the shadow would be distorted. But they go straight, and the shadow is crisp. You cannot see around corners. If someone is standing behind a wall, the little bullets from the lamp fly past in straight lines and never reach the person. They are in the dark. No photon makes a left turn. A beam of light through fog or smoke, you have seen this. A shaft of gold cutting through the mist. Why can you see the beam? Because the little bullets are bouncing off the tiny water droplets, scattering in all directions, and some of them scatter into your eye. Without the fog, the bullets go straight from the flashlight to the wall, and you never see them in transit. With the fog, they scatter, and you see a glowing rod. Beautiful. Explained. Reflection. A photon comes in, hits a mirror, bounces off. The angle it comes in at equals the angle it leaves at, just like a tennis ball bouncing off a hard floor. If you throw the ball at 45 degrees, it leaves at 45 degrees on the other side. The ancient Greeks knew this. Hero of Alexandria around the 1st century even proved something remarkable. The path the photon takes, hitting the mirror and bouncing to your eye, is the shortest possible path between you, the mirror, and the source. The photon is being efficient. It is optimizing its route, like a delivery driver who knows the shortcuts. Now let us talk about refraction, because this is where the bullet picture really shines, ironically enough. Refraction is the bending of light when it enters a different material. Stick a straw into a glass of water. Look at it from the side. The straw appears to break at the water surface. It looks crooked even though you know it is straight. That is because light from the part of the straw underwater is bending as it exits the water, and your eye traces the light back in a straight line and gets fooled about where the straw is. There is a precise law governing this bending, discovered by Willebrord Snell around 1621. It relates the angle of the incoming light to the angle of the refracted light using the speeds of light in the two materials. Beautiful, clean mathematics. But the truly elegant thing, the thing that makes the whole picture feel airtight, is Fermat's principle. Pierre de Fermat in the 1630s proposed a radical idea. Light always takes the path of least time. Light is in a hurry. Given a choice of routes, it picks the fastest one. If the light is traveling through empty space, the fastest path is a straight line, because any detour adds distance and therefore adds time. If the light has to bounce off a mirror, the fastest path is the one where the angle of incidence equals the angle of reflection, because Hero already proved that is the shortest distance. And if light passes from one material to another, from air into glass for instance, the fastest path is not a straight line because light moves slower in glass, so the optimal route involves spending more distance in the fast material and less distance in the slow material, which means the path bends at the boundary, and the amount of bending is exactly what Snell's law says. Let me give you the analogy that makes this vivid. Imagine a lifeguard sitting on a beach, on a tall chair, looking out at the ocean. Off to the right, diagonally, there is a swimmer in trouble, screaming for help. The lifeguard has to get there as fast as possible. Now, the lifeguard can run on sand at, say, 15 feet per second, but the lifeguard can only swim at 5 feet per second, 3 times slower in the water. What is the fastest path? A straight line? No. A straight line from the chair to the swimmer spends too much time in the water where the lifeguard is slow. What about running all the way down the beach until the lifeguard is directly opposite the swimmer and then swimming straight out? No, that wastes too much time running sideways on the beach. The optimal path is a compromise. Run along the beach for a while, getting closer to the swimmer, and then cut into the water at an angle. Not too steep, not too shallow. If you do the calculus, if you minimize the total time, the optimal angle at which the lifeguard enters the water satisfies exactly the same formula as Snell's law of refraction. Light behaves exactly like a lifeguard who is very good at math and extremely motivated. And I should mention, the bullets come one at a time. This is important. If you dim the light enough, you can send photons one by one through the apparatus. You hear individual clicks in the detector. Click, click, click. Not a continuous hiss. Individual, distinct clicks. Each click is one photon, one little bullet arriving. So light really does come in lumps, individual particles. The clicks prove it. Newton was right about that much. This makes the bullet picture even more convincing. You see, because if light came in continuous waves, like ocean waves, you would expect a detector to register a smooth, continuous signal. Instead it clicks, one quantum at a time, one photon, one bullet. So when I tell you the bullet picture is wrong, I am not telling you that light is not made of particles. It is made of particles. We hear the clicks. What I am telling you is that the particles do not do what you think they do between one click and the next. Between emission and detection, something very strange is going on, something the bullet picture simply cannot accommodate. Let me also mention one more thing the bullet picture handles well, because I want you to feel the full weight of how good the wrong idea is before I crush it. Colors. White light is a mixture of all colors. When white light hits a prism, the different colors refract by different amounts. Red bends a little, violet bends a lot, and you get a rainbow. In the bullet picture, different colored photons travel at different speeds in glass. Red photons go a bit faster, so they bend less. Violet photons go slower, so they bend more. That gives you the rainbow. Lovely. And the photoelectric effect. Shine light on a metal surface and electrons come flying out, but only if the light is above a certain frequency. Red light, no matter how bright, produces no electrons from certain metals. But dim violet light ejects them immediately. In the bullet picture, each photon carries a lump of energy, and the energy depends on the color. Violet photons carry more energy than red photons. If a single photon does not carry enough energy to knock an electron loose, no amount of red light will do it. But a single violet photon has enough punch. This is exactly right. Einstein figured this out in 1905, and it won him the Nobel Prize. So the bullet picture handles shadows, reflection, refraction, rainbows, the photoelectric effect, and the click-by-click arrival of individual photons. It is an extremely good picture. You would be perfectly justified in being attached to it, which is why what I am about to tell you is so disturbing. Pick up a piece of glass. flat, clean, ordinary glass. Both surfaces are polished parallel. Now shine a beam of monochromatic light, single color light, straight at it, perpendicular, head on, not at an angle, straight in. Most of the light goes through the glass, but some fraction reflects back. About 4% of the light bounces off the front surface. We can measure this with great precision. If we dim the beam until individual photons are arriving one by one, we count 4 reflections out of every 100 photons. 4%. Some photons pass through the front surface, travel through the interior of the glass, and hit the back surface. About 4% of those reflect off the back surface and come back the way they entered. So there are 2 reflections, front surface and back surface. If these are independent events, like rolling 2 dice, you expect the total reflection to be about 8%. 4 from the front plus 4 from the back. Maybe a hair less than 8 because the second 4% applies to the 96% that made it through the front, not the original 100%, but roughly 8%. That is not what happens. The total reflection depends on the thickness of the glass. And it does not just vary a little, it oscillates. For certain thicknesses, the total reflection is 0. Not close to 0. 0. Every photon goes through. For other thicknesses, the total reflection is 16%, double what you expected from simple addition. And as the glass gets gradually thicker, the reflection cycles smoothly from 0 to 16, back to 0, up to 16, 0, 16, over and over. This is not a subtle effect, it is not a small correction. It is the difference between no reflection at all and reflection that is double the obvious prediction. And it has been measured with lasers through more than 50 meters of glass, cycling perfectly, more than 100 million repetitions, and the pattern holds without fading. Let me put some numbers on this so you feel the strangeness concretely. The distance the glass has to thicken to go through one complete cycle, from maximum reflection back to maximum reflection, is related to the wavelength of the light. For red light, the wavelength is about 700 nanometers. For blue light, about 400 nanometers, so the cycle is shorter for blue light than for red. And if you use white light, which is a mixture of all colors, the different colors cycle at different rates, and they blur each other out, and the reflection settles to a mushy average around 8%. Which is why in ordinary life, with ordinary light and ordinary glass, you never notice the oscillation. You just see a faint reflection, about 8%. Consistent with the simple addition of 4 and 4, but the oscillation is there. Under controlled conditions with a single wavelength, it is perfectly visible, perfectly regular, and it tells you something is very wrong with the simple picture. And here is what really rattles people. This is not some new discovery. Isaac Newton himself noticed it. He measured the reflection from thin glass plates and saw the oscillation. He called them fits of easy reflection and easy transmission. The glass seemed to switch between moods, a reflecting mood and a transmitting mood, in a regular cycle that depended on the thickness. Newton measured the cycle length with extraordinary precision, but he could never explain it. He tried, he wrote pages and pages about it, inventing elaborate theories about dispositions and vibrations associated with the corpuscles. But within the bullet picture, there simply is no explanation. The best he could do was describe the pattern and move on, leaving it as one of the deepest puzzles of optics. 300 years later, we can explain it, but only by abandoning the bullet picture entirely. Now I want you to think very carefully about what this means for the little bullet picture. A photon arrives at the front surface. It is about to decide whether to bounce off or pass through. In the bullet picture, this decision happens at the front surface. The photon interacts with the atoms at the surface and either reflects or transmits, but the outcome of that decision, the probability of reflection, depends on the thickness of the glass. It depends on where the back surface is, a surface the photon has not encountered yet. How does the photon know? It is at the front surface. It cannot see the back surface. It has not traveled through the glass yet. Nobody sent it a memo about the glass thickness, but its probability of bouncing depends critically on that thickness. Change the thickness by a tiny fraction of the wavelength of the light, and the reflection probability swings from 0 to 16%. This is like a coin that, when you flip it, knows whether it is going to land heads or tails based on how high the ceiling is, even though the coin never touches the ceiling. Some people try to fix the bullet picture. Maybe the photon enters the glass, rushes to the back surface, bounces back, and this round trip somehow telegraphs information to the front surface before the photon decides. But the experiments say no, the front surface reflection is instantaneous. There is no delay that corresponds to a round trip at the speed of light through the glass. Whatever is happening, it is not a bullet doing reconnaissance. The bullet picture cannot explain this. Something fundamental is wrong. Let me push you over the edge completely. There is another experiment that makes the problem even worse. Take a mirror, a nice flat rectangular mirror. Set up a light source on one side and a detector on the other side, arranged so that light bouncing off the center of the mirror reaches the detector. Standard geometry. The angle at the center obeys the law of reflection. Perfect. In the bullet picture, photons hit the center and bounce to the detector, and everything else on the mirror is irrelevant. Test it. Cover up the far left and right sections of the mirror with black tape. The light still arrives at the detector. The center is doing the work. The edges do not matter. So far so good for the bullet picture. But now try something different. Do not cover the edges with tape. Instead, carefully etch grooves into the mirror surface at the far left and far right. Not random scratches. A diffraction grating. Precisely spaced lines. When you do this, light reflected from those far edges, from the sections where the reflection angle is completely wrong for reaching the detector, shows up at the detector. This is baffling. In the bullet picture, photons bouncing off the far left of the mirror should be going off at an angle that misses the detector by a wide margin. The geometry forbids those photons from reaching the detector, but they arrive. The only possible explanation is that photons were already going to the far edges. They were already reflecting off every point on the mirror, including points where the angles should not work. But their contributions were invisible because they were canceling each other out. Imagine the mirror divided into thousands of tiny strips. Each strip reflects light to the detector, and each reflection contributes a little arrow. At the center of the mirror, the arrows from neighboring strips point in nearly the same direction. They add up, strong signal. At the edges, the arrows from neighboring strips spin rapidly in direction, one pointing north, the next south, the next east. When you line them up head to tail, they spiral around and go nowhere. Total contribution 0. The grating removes selected strips. It eliminates every other arrow. Without their canceling partners, the surviving arrows at the edges no longer spiral to nothing. They add to something. Light from the wrong angles appears at the detector. The mirror was reflecting from its entire surface all along. You just could not see it, because the contributions from the edges were hiding behind perfect cancellation. Let me give you one more example to drive this home, because I think it is the most shocking of all. It comes from the double slit experiment. You have a source of light and a screen with two narrow slits in it. Beyond the screen is a photographic plate or a detector array, something that records where photons land. In the bullet picture, each photon goes through one slit or the other. Half go through the left slit, half through the right. And on the detector, you would expect to see two bright bands, one behind each slit. The bullets go through the slits and hit the wall directly behind. But that is not what you see. You see an interference pattern. Bright bands alternating with dark bands spread across the detector. Some spots get hit a lot. Other spots equally accessible from both slits get hit not at all. The dark bands are places where, somehow, the presence of two open slits produces less light than one open slit alone. Closing one slit can actually increase the light at certain spots. In the bullet picture, this is impossible. Two open holes should always give more light than one open hole. You cannot add bullets together and get fewer bullets. But with light, you can, because you are not adding bullets. You are adding arrows. Each slit provides a set of paths from the source to the detector. Each path contributes an arrow. The arrows from paths through the left slit point in certain directions, depending on the travel times to different spots on the detector. The arrows from paths through the right slit point in other directions. At some spots, the arrows from the left slit and the arrows from the right slit point in the same direction. They add up, bright band. At other spots, they point in opposite directions. They cancel, dark band. The missing light at the dark bands is not missing. It has been cancelled. The arrows from the two slits at those particular spots point opposite and destroy each other. The photon is not avoiding those spots, it is that the amplitudes from the two paths add to 0 there. And it gets stranger. Dim the light until you are sending photons one at a time. One photon passes through the apparatus. It lands somewhere on the detector. Click. Send another. Click. One by one, over hours and hours, the photons accumulate. And slowly, point by point, the interference pattern emerges. Each individual photon is a single click at a single spot. But over many photons, the pattern is the same interference pattern you would get with a bright beam. The pattern is statistical, but it is precise. The photon is an individual particle. It makes a single click, yet its behavior is governed by the arrows from all paths through both slits. Even though it is a single indivisible quantum, its probability of landing at any given spot depends on both slits being open. Block one slit, and the pattern changes. The photon, passing through one slit, knows whether the other slit is open. In the sum over paths picture, this is natural. The photon does not go through one slit. It does not go through both slits. It explores all paths, including paths through both slits, and the arrows from all those paths combine to create the interference pattern. The dark bands are where the arrows cancel. The bright bands are where they add. A single photon lands according to the probability given by the total arrow at each spot, and over many photons the pattern reveals itself. There is no paradox if you give up asking which slit the photon went through. The question which slit assumes the photon had a definite trajectory. It did not. It had arrows from all paths. The arrows are the whole story. And if you put a detector at one of the slits to catch the photon in the act and find out which one it went through, the interference pattern vanishes. It vanishes because the detection creates a new event. It collapses the sum over paths into a much smaller sum, and the beautiful cancellation that produced the dark bands is gone. You get the answer to which slit, but you lose the interference. You cannot have both. The universe makes you choose between knowing the path and seeing the pattern. This is the heart of quantum mechanics, and it comes straight out of the sum over paths. There is no separate measurement postulate or wave function collapse that you need to add by hand. The rules are simple. All paths contribute. Add the arrows. Square the total. If you constrain which paths are available, by closing a slit or putting in a detector, you change the sum, and you change the result. So the bullet picture is dead. Let me tell you what takes its place. A photon going from a source to a detector does not take one path. It takes every path, every conceivable trajectory through the entire universe. The straight line, yes. Also the path that curves slightly left, the path that goes up to the ceiling and back down, the path that loops around the building, the path that goes to Mars, the path that visits the Andromeda galaxy. Every path, without exception, contributes to the final result. Let me be very precise about what I mean by every possible path, because I think people hear that phrase and their imagination gives up too soon. I do not just mean every straight line from A to B that goes through different intermediate points. I mean every path, curved paths, zigzag paths, paths that go backward before going forward, paths that loop in circles, paths that go from New York to the detector by way of Tokyo, paths that leave the Earth, fly to the moon, circle it twice, come back, bounce off a fire hydrant, and arrive at the detector. Every continuous curve connecting the source to the detector, no matter how absurd, contributes an arrow. You might think that including the path through Tokyo is a mathematical formality, that its contribution must be so ridiculously small that it does not matter. And you are right that it does not matter, in the sense that it has no measurable effect on the final answer. But it does not fail to matter, because the path is excluded. It fails to matter because its arrow is cancelled by the arrows of neighboring paths. The path through Tokyo is included in the sum. It contributes its arrow. But the path that goes through Tokyo via a slightly different route contributes an arrow pointing in a very different direction, and those two arrows destroy each other. And the path through Osaka destroys another, and so on. The cancellation is what makes those paths irrelevant, not any rule that says they are forbidden. This is a very important distinction. The theory does not say only reasonable paths contribute. The theory says all paths contribute, but unreasonable paths cancel. These are very different statements. The first would mean you could safely ignore the crazy paths. The second means you cannot. The crazy paths are doing crucial work. They are canceling each other. If you leave them out of the calculation, you lose the cancellation, and you get the wrong answer. There is an analogy that might help. Imagine 1,000 people standing around a circular track, each holding a rope tied to a post in the center. If they all pull outward in their respective directions, the post does not move. The forces cancel. But every person is pulling. Every person is doing work. You cannot say only the person pulling north matters, because the post is not moving north. It is not moving at all. Precisely because everybody is pulling, the zero result requires everyone's participation. The same is true for the crazy paths. The zero contribution from the path through Andromeda is not a nothing happened. It is the result of furious, meticulous cancellation among all the paths in that region. The nothing is built from something. This is why, when you put a diffraction grating on a mirror, you can make light appear from angles where it should not come from. You have disrupted the cancellation. You have fired some of the people around the track, and now the remaining people's pulls do not cancel and the post moves. The whole fabric of classical optics, every straight beam, every sharp shadow, every clean reflection, is held in place by the cancellation of everything else. It is a tapestry woven from destruction. Each path carries a little arrow. Here is how the arrow works. Imagine a tiny stopwatch spinning incredibly fast. The speed of spinning depends on the color of the light. Blue light makes the hand spin faster than red light. The stopwatch starts when the photon is emitted. As the photon travels along some particular path, the stopwatch spins. When the photon arrives at the detector by that path, the stopwatch stops. The direction the hand is pointing is the direction of the arrow for that path. The length of every arrow is the same. This is crucial. No path gets a bigger arrow. No path is inherently more likely in terms of its individual contribution. The only thing that differs between paths is the direction of their arrows, and the direction is entirely determined by the travel time. A short path like the straight line from source to detector stops the stopwatch quickly. The hand has not had time to spin far. A nearby path, one that is almost straight but bows out slightly, takes almost the same time and stops the stopwatch at almost the same position. These arrows point in nearly the same direction. A crazy long path, one that goes to Andromeda and back, stops the stopwatch after trillions of revolutions. A slightly different crazy path stops it after a slightly different number of trillions of revolutions. But after trillions of revolutions, even a tiny difference in the number of revolutions means the hand ends up pointing in a completely different direction. Imagine a clock hand that spins 1,000,000 times. Now imagine it spins 1,000,001 times. That extra revolution puts the hand in a different spot. The arrows from crazy paths point in effectively random directions. To find the total probability of the photon reaching the detector, you take all the arrows, one from every possible path, and add them head to tail. The final arrow from the starting point to the end point of this enormous chain gives the total amplitude. Square its length to get the probability. The arrows from crazy paths add up to nothing. One points up, the next points down, the next points sideways. 1,000,000 arrows in random directions added head to tail trace out a random walk that ends up almost exactly where it started. Their net contribution is zero. They cancel each other out. But the arrows from paths near the straight line add up to something big. They all point in nearly the same direction. 100 arrows all marching northeast added head to tail make one long arrow pointing northeast, a real substantial contribution. So the total result is dominated by the neighborhood of the straight line path. Not because the photon chose it, not because somebody pointed the photon in the right direction, but because every other option destroyed itself. The straight line is the path of agreement. Everything else is the path of discord. Agreement survives. Discord cancels. This is not poetry. This is the calculation. You sit down and do the math, and you get the exact answer for every experiment with light ever performed. Every single one, no exceptions. Let me go back to our two mysteries and show you how this resolves them. The glass plate, a photon going from the source to a detector positioned to catch reflections, has two main families of paths. One family bounce off the front surface. The other family pass through, bounce off the back, come back out. Each family produces an arrow. Both arrows have roughly the same length, about 0.2, because the probability of reflection from a single surface is about 4%, and the square root of 4% is about 0.2. What matters is the direction of the arrows. The front reflection arrow points in some direction determined by the travel time along that path. The back reflection arrow points in a direction determined by its travel time, which is longer because the photon crosses the glass twice. How much longer depends on the thickness. If the thickness is just right, the extra time makes the back reflection arrow point in the same direction as the front reflection arrow. Add two arrows of length 0.2 pointing the same way and you get an arrow of length 0.4. Square that and you get 0.16. 16%. If the thickness is different, the extra time rotates the back reflection arrow to point opposite the front reflection arrow. Two arrows of length 0.2 in opposite directions sum to 0. 0% reflection. As the thickness gradually changes, the back reflection arrow slowly rotates relative to the front reflection arrow, and the total oscillates 0 to 16, back to 0, over and over, exactly matching the experiment. No mysterious knowledge, no signal from the back surface, just arrows, added according to their travel times. The photon does not need to know anything. It explores all paths, and the arithmetic does the rest. The mirror works the same way. Every point on the mirror contributes an arrow to the sum. At the center, the arrows from nearby points agree in direction and add up. At the edges, they disagree wildly and cancel. The grading removes half the arrows at the edges, breaking the cancellation, and the remaining arrows add up to something visible. Everything we observed, every strange result, follows from one rule: sum over all paths. Add the arrows, square the result. Now let me show you the deepest layer, the part that connects quantum mechanics to the classical physics you already know. Fermat's principle. Light takes the path of least time. For 300 years, nobody could explain why. It was beautiful but mysterious. Was light intelligent? Did it plan ahead? How could a mindless beam of light figure out the fastest route? The sum over paths answers this completely. Light explores all paths. The path of least time is special, not because light prefers it, but because of a mathematical property of minimums. At a minimum, the function is flat. Small changes in the path produce small changes in the travel time, so nearby paths all have nearly the same time, which means nearly the same arrow direction, which means they add constructively. Away from the minimum, the travel time changes rapidly, with small changes in the path. Nearby paths disagree in their arrow directions and cancel. Only the neighborhood of the least time path survives the destruction. Fermat's principle is not fundamental. It is not the explanation. It is the consequence. The quantum sum over paths is the explanation, and Fermat's principle is what it looks like from far away. And the same story plays out in all of classical mechanics. There is a principle called the principle of least action. Every classical trajectory, a thrown ball, a planet in orbit, a pendulum swinging, minimizes a quantity called the action. This has been known for centuries, and for centuries it was unexplained. Why should nature care about minimizing an abstract integral? Because nature does not minimize anything. At the quantum level, the ball explores every trajectory. Each one contributes an arrow. The arrow's direction is set by the action along that trajectory divided by Planck's constant. Planck's constant is about 6.63 times 10 to the minus 34. For a macroscopic ball, the action is incomprehensibly large compared to this number. A tiny change in the trajectory causes an enormous change in the arrow direction. The arrows from non-optimal trajectories spin like deranged weather vanes, and they cancel each other perfectly. Only near the trajectory that minimizes the action do the arrows agree, because at the minimum the action changes slowly. When you tweak the path, nearby trajectories have nearly the same action, nearly the same arrow direction, and they add up. Newton's laws are not fundamental. They emerge from the quantum sum over all trajectories in the limit where Planck's constant is negligibly small. The classical world, with its definite paths and deterministic equations, is the residue of quantum cancellation. It is what is left when everything else has destroyed itself. This unification has a kind of mathematical elegance that still gives me chills. Let me spell it out. In the quantum calculation, each path gets assigned a little arrow whose direction is determined by the action along that path divided by Planck's constant. The magnitude is always the same, only the direction changes, and the direction spins as the action changes. For a macroscopic object, the action is something like 1 joule-second for a typical motion. Planck's constant is about 6.63 times 10 to the minus 34 joule-seconds. So the ratio, the action divided by Planck's constant, is something like 10 to the 34th. That is 1 followed by 34 zeros, a number so large it defies comprehension. That means the arrow's direction, which is proportional to this ratio, changes by a full revolution when the action changes by a tiny amount. A change in action of 6.63 times 10 to the minus 34 is enough to spin the arrow all the way around. That is so small that even the tiniest variation in the path produces wild changes in the arrow. The arrows from non-optimal paths oscillate at incredible speed, and they average out to exactly 0. But at the path of least action, the action is stationary. So pushed, it is flat. A small change in the path produces no first-order change in the action. The arrows stop spinning, they sit still, they agree, and they accumulate into the one big arrow that determines the classical trajectory. So the classical world is not an approximation to the quantum world. It is an exact consequence of the quantum world in the limit where the action dwarfs Planck's constant. The uncertainty and the fuzziness and the multiple paths do not go away for big objects. They are there, but the cancellation is so perfect, so complete, so thorough, that the fuzziness is smaller than anything you could ever measure. The classical world is quantum mechanics with the volume turned up so high that all the dissonance cancels and only the melody remains. But turn the volume down, make the object small, make the action comparable to Planck's constant. Now the arrows from different paths no longer spin wildly relative to each other. They can disagree modestly without cancelling. Multiple paths contribute. The particle no longer follows a single trajectory. It spreads, it interferes, it behaves like a photon going through two slits, or an electron tunneling through a barrier. The quantum weirdness reveals itself. The boundary between the quantum world and the classical world is not a wall. It is a volume knob. And Planck's constant sets the threshold. The world you see, where balls follow parabolas and planets trace ellipses and light goes in straight lines, is a shadow. The substance is the quantum arithmetic of arrows. The shadow is sharp because cancellation is thorough. But the shadow is still a shadow. So let me answer the question we started with. How does light get from the sun to your eye? There is no golden bullet flying through space. Between emission and detection, the photon does not have a position. It does not have a trajectory. It does not occupy successive points along a path. What exists is a probability amplitude, computed by summing arrows from every conceivable path, the straight line, the detour through Mars, the loop around the galaxy. All of them contribute. The crazy ones cancel. The sensible ones survive. And the result is indistinguishable from a beam of light traveling in a straight line at 186,000 miles per second. The appearance of travel is real. The warmth on your face is real. But the underlying picture, the story of a particle in flight, is an approximation, a fantastically successful approximation that works for every practical purpose, but not the truth. People want to know what the photon is doing between emission and detection. And I tell them honestly, the theory does not say it gives you the probability of detection. It does not give you a movie of the journey. If you place a detector in the photon's path, you create new events of emission and detection. You get different results. The in-between is not hidden. It is not there. Some people find this infuriating. They want a picture, a narrative, a comfortable image of a little particle cruising through space. And I sympathize. But nature is not obligated to satisfy our desire for stories. Nature is what it is. Our job is to describe it accurately. And the accurate description is sum over all paths. Add the arrows, square the result. How accurate? Let me tell you, because I think people do not always appreciate what this theory achieves. The magnetic moment of the electron has been measured to extraordinary precision. The theoretical prediction from QED involves computing Feynman diagrams, which are really just pictorial representations of different ways to sum over paths, with the photon and the electron interacting in various complicated loops. The simplest diagram gives you a rough answer. Add the next diagram, a loop with one extra photon, and you get a correction. Add the next more loops, more photons, and you get a finer correction. Each correction is smaller than the last. When you add up enough diagrams, you get a number. And that number, when compared to the experimentally measured value, agrees to about 1 part in 10 to the 10th power. That is 1 part in 10 billion. Let me say that differently. Imagine you have a ruler that is long enough to stretch from one side of the United States to the other, roughly 3,000 miles. 1 part in 10 billion of 3,000 miles is about the width of a human hair. That is the level of precision at which QED agrees with experiment. There is no other theory in any branch of science that has achieved this. The general theory of relativity has been tested to maybe 14 decimal places in some gravitational wave measurements, which is extraordinary. But in terms of the sheer range and variety of predictions that have been checked, QED has no rival. And the whole thing, every last decimal place, comes from the sum over paths. Add the arrows, square the result. That is the rule that produces the most precise predictions in the history of science. So when people tell me the sum over all paths is just a mathematical trick, the photon really goes in a straight line, I say, show me your trick that predicts the electron's magnetic moment to 10 decimal places. because my trick does. So here is my parting thought, and I want this to stay with you because I think it is one of the most remarkable facts about the universe we live in. Every time you see a beam of sunlight coming through a window, every time you watch light bounce off a mirror or bend through a glass of water or cast a shadow on a wall, you are watching the aftermath of infinite destruction. Of an incomprehensible number of possible paths were explored, their arrows were computed, and almost all of them cancelled each other into nothing. What survived the destruction is the beam you see, the shadow you see, the reflection you see, the rainbow in the oil slick, the sparkle in a diamond, the blue of the sky, all of it. Every optical phenomenon in your daily experience is the thin surviving residue of a vast quantum computation that destroyed almost everything it created. The straight line is real, the beam is real, but it is not chosen. It is what remains after everything else has been annihilated by interference. It is the last man standing in a fight involving an infinite number of combatants. And this is not just about light, this is about you, about the chair you are sitting in, about the ground under your feet. Every particle of matter in the universe obeys the same rule. Sum over all paths, add the arrows. The classical world, a solid, reliable, sensible world of trajectories and forces and causes and effects, is the surviving shadow of a quantum reality in which all possibilities are explored and almost all are destroyed. The classical world of light, with its straight lines and sharp shadows and simple rules, is the residue. It is what remains after the cancellation. And if light does this, then so does everything else, because the same quantum rule governs all particles. The solid, predictable world you inhabit, where objects follow trajectories and causes produce effects, is the sum over all possibilities, with nearly everything subtracted. What are those cancelled possibilities? Are they real? Were they ever real? Or are they bookkeeping, mathematical scaffolding that serves the calculation and nothing more? That is a question I have turned over in my mind for a long time. I do not have a satisfying answer, but I believe whoever finds the answer will have discovered something extraordinary about the nature of existence itself. Think it over tonight. I would love to hear where your thinking takes you.